So I'm Richard Berry, one of the scientists in Dave Bennett's gravitational microlensing working groups, a group at Goddard Space Flight Center. In my capacity as a member of that group, I've been working for a while now on exploring a space of opportunities to fly a space mission to obtain masses of bound and free-floating planets when working with Roman Space Telescope and ground observatories. So I've been working on this for quite a number of years, since 2015. We first start here with a kind of a zeroth level question about how many masses we would really have to obtain in order to be able to begin to say something about planet formation theory, to begin to calibrate planet formation theory. So we have a theorist in our group, Sean Raymond, and he did this analysis where he takes models of known planets and applies an n-body simulation and accumulates a number of planets that survive and a number of planets that are ejected from those systems by those interactions as the systems become dynamically relaxed. And then we run a Kolmogorov-Smirnov test to see if the eventual those two ensembles of planets were drawn from the same set or different sets. So whenever the KS metric drops below 1%, then we know that these are distinct sets. So we did this, and if you have very low mass, if you have very low mass uncertainty, perfect mass measurements, it only takes 10 or 20 masses before you can start to see these belong to two different sets. You have free-floating planets and bound planets. And as you add increasing noise to the measurement, you need a pace, you need more and more measurements, just as you would expect. Now, I should have done that before. Now we add a population, another noise figure, which is a population of planets that form in space by the same processes that form stars. And for this, we call these NACOs, which is a non-fusing autochthonous compact object, which captures all of the masses out in space that are not stars. So you add a population of those in there. If we assume that there's 50% contribution of these tiny stars or failed stars across the full mass range, you end up having to have a couple of hundred mass measurements before you can begin to discriminate these two sets. But we expect, or theory suggests, that it's something closer to 25% of these NACOs are to be added to the set. And when you do that, you need between 80 and 100 mass measurements to be able to discriminate those two sets, free floaters from planets that form out in space, to 95% confidence level. So in order to do that, we need to measure the masses of especially these very low mass planets floating in space. And this is now a well-known result from Johnson et al. 2020, where Roman Space Telescope's sensitivity to these low mass planets kind of falls off a cliff below Earth mass. And that's principally because this Johnson et al. Argued compellingly that you need 6 measurements across each of these events in order to allow you to estimate the Paczynski parameters. So T naught, TE, and the impact parameter. So as a consequence, the sensitivity drops way off. And if you just start to increase the cadence of the observations, eventually you run into the ref stall limits on parallax, to where the observatory at L2 won't observe the same event as the Earth will. So we have been working on this for some time. It's been 7 different grants to start to develop this idea from back right after we did David Bennett and a group of folks back in 2011 used the deep impact flyby spacecraft to do the first simultaneous measurement from space and ground to estimate the mass of a planet. And that was Meraki et al. 2011, which is a 10 Earth mass planet or failed Jupiter core that looked like this. And so this is an example of where we're up against a Refstall limit of the parallax, and the two curves are almost on top of each other. And so it didn't really help the mass estimate that much, but it was worthy. And it was quite a lot of effort that went into that. The deep impact flyby spacecraft had a significant chromatic defocus anomaly that was very difficult to work with. You had to do deconvolutions and everything to retrieve the signal in a very crowded field. And since then, we have developed something called Ramjet, which is artificial intelligence code. I started this back before TESS flew, and it was originally a support vector machine that didn't work very well. We hired two postdocs, and now Stella Ishitani Silva and Greg Olmschenk, who have transformed this into a PyTorch-based neural network that can inference on individual light curves in 50 milliseconds. Pretty amazing. So it has found almost 200 transiting planets in the test set. 7 out of 8 of them are now confirmed planets. So that's a major coup there. And so Stella and Greg are now taking this code and they're adapting it to finding gravitational microlensing signals in these large data sets. So we expect that this is going to be very important for us going forward with Roman. So we have also been working on running these codes on small, compact, fanless GPUs that you use in industrial controllers to see if we can do this in space, to inference in space and be able to identify things on the fly. So that what you see there is at the Sibley Memorial Hospital. It's a medical device to throw hot protons at people with cancer. We put these parts in there and run Ramjet on all of them to see if some of these will survive, and it did not affect the inferencing capabilities of these, which is pretty amazing. Now, also during this effort, we worked with Lawrence Livermore National Lab to have a telescope, and this is a 1/5 scale model of that telescope. They named it a CLEoscope. So this is the actual scope is 47 centimeters in diameter, has a focal length of 200 centimeters. The whole thing will weigh about 80 kilograms, and it's only 12 and a half centimeters deep. So fairly amazing piece of work. And that is being space qualified now. So we're working towards space qualification of this new type of design. We have one that is a TRL-9 that has already flown in space. It's a 20 centimeter version of this. So enabling technology. So the ConOps that we had settled on was that CLEoPATRA would have this 1.6 degree square field of view, and we would park it on top of the Roman field of regard and integrate for a long time. And so we should be able to pick up a number of these down to magnitude of 23 AB. So we also engaged our Roman Galactic PIC collaborators, Johnson and Rattenbury. They performed image level simulations and figured out how many detections, how many of these were detected by both Roman and CLEoPATRA simultaneously, and evolved this chart. And so 80 simultaneous detections with Roman in this mass range allowing the ejected and in situ population to be detected at 95% confidence. Pretty good piece of work there. So we ask, what is the path forward for this? How can we best help the measurement? So this is a representation from Gould plus 2024 and Gould's 2024, showing the ref stall limits in red. So that's the ref stall limits in the Parallax. So on the one end, you end up with the light curves right on top of each other. On the other end, you end up with light curves being observed by one observatory and not the other one. Ptaschinski limit, which is a limit on the Einstein ring size, that the angular Einstein ring. Below a certain point, you're no longer able to measure the Ptaschinski parameters. And so this shows that the projected baseline from L2 to Earth gives you an entire swath of planets centered on Earth masses. And you'll see that it dips down approximately down to Mars's. But if we add an additional observatory in geostationary orbit, then we can get this entire body of very small mass planets, free-floating planets, from exoplutos to Earths, and fill in the bottom part of that mass spectrum. So we think that this is a worthy space mission concept and would like to continue to pursue it, and are interested in the community's feedback. So here are the key takeaways that I want you to take away from this. Augmentation of Roman galactic bulge time domain survey is necessary to estimate these masses. And we can do this even in the presence of these compact objects that have formed in space. And we can do this with a space mission that's about 1% to 2% of the cost of Roman. And we could get this entire range of masses that are very critical. The masses between Earth and Pluto have particularly high theoretical leverage on planet formation theory. So in order to obtain these, we have to have the correct baseline and the correct cadence. So it's going to be, and then this is the crew of folks that I've gotten to work with on this, and it has been a sustained bit of work since 2015. And that's the end of my talk, but I'd like any questions or comments.
Is it funded? Is it funded?
It is not at present. I have nothing. Yeah. Oh, scheiße. So we have proposed this already to NASA Goddard Astrophysics Science Division. They chose not to support it because it depended on on an extended mission for Roman, which you can't propose for. But this new design that works primarily with ground observatories, or possibly a LEO observatory, would benefit by the existence of the extended mission of Roman, but doesn't depend on it. So you can get these Pluto to Earth masses without Roman being in the picture. So we are going to continue with it, continue seeing if there's a window to propose this. I'll leave this model out here if you're interested in looking at it. It's a model of our telescope called the CLEoScope.